Well, let's see how this music pans out. So I'm going to look up, we're going to look up something. I don't know how long I'm going to be doing this. Is another short stream. Because I wasn't feeling all that good, so I said, you know what, I can't go to work, but I might feel better in a couple hours. I'm going to just do something really kind of quickish on here, and then go lay down before I can see if I can go to work. So the first thing I want to do is I want to look up, I mean, I got this information in my books, but I want to see if I can find it on here. Why doesn't that show up? Or does it? Okay, so non-linear dampening equation. Of course you couldn't find it. Because you're not as smart as I am. I may have to go to my book to find it. Because it's all bullshit that they got in here. Where's my book? You know, I may have to. Because I'm looking for a certain equation. It's really simple. It's not all this bullshit that they got in here. Let's see. Nonlinear system. Dampening equation. With dampening term. D squared x over dt squared mckx. Where f of x is the dampening effect, I'm looking for a certain equation in this system. Dampening force. No, it's not here. There's a PDF. Yeah, I don't know. What are you gonna do, huh? No, that's not it. That ain't gonna be it. Jesus, look at this bullshit. Okay, is this the spring? Aha. It represents a particular coordinate transformation. Allows dynamical system to be modeled by a truncated set of uncoupled oscillators. Uncoupled oscillators. Well, that's bullshit because this is I wonder if we type in nonlinear system equated with damping with damping term in a feedback loop. I'm gonna have to get my book. Second order system with state feedback. You know, I may have to get my book because I can't find it here. It's a simple equation. You know what? I'm gonna have to get my book. So, let me, I'm just gonna go ahead and we'll just pop the pyramid up here. Actually, you know what? Better yet, let me just do this here. I want to get my book, and I'm going to have to get a refill. Probably have to have the light on. I think I can find that book. I got two books. I think it's in the second book. I just gotta check something really quick. And I will be right there. Okay, that's looking good. That's looking good. All right, grab this. Just gonna set this drink down so I don't spill it. I have a book that's called Nonlinear Systems and Second Order Differential Equations or something like that. I don't think it's in that pile. I got one of them. I think it's the red book. It's a very basic equation. Oh, I think I found it here. I knew I left it out. I left it out because I was pretty sure that I was going to be needing it. Well, excuse my... I might plop my wonderful picture back up on here. Turn this on. I want to hear my music. That could be a problem. Alright, so let's see if we can find this here. It's called a transient response. Talks about reducing, increasing K. Well, I don't know what that shit's all about. So filters have a transient response. Frequency response in the system. Stability. So there's a stability section. There's things that have to do with differential equations, simple ones, where numbers equal 0, -1, or infinity, and it determines a type of stability. Jesus. So it looks like what I'm looking for. So you could have a square wave, and if square wave gets filtered out, and on the edges, on the top edges of the square wave, there's a transient response, which tells you about the information about the square wave, how good it is and such. There's a settling time, they call it settling time, yada yada. Small, not desirable because of the fast rise time. They result in excessive overshoot and lengthy settling times. The range 0.3, I think it's, I don't know what the fucking name of that sign is. Analysis of second order systems. System transfer function. How would I see that damn transient response thing? Damn it, fuck yeah. 150. There's 2 pages here. What the fuck? Are you fucking shitting me? There we go. Yeah, the transient response. The form of the transient response can only be determined without solving equations. The denominator of the transfer function completely describes the transient response because the denominator is always the characteristic equation of the system. You've got delta m of s equals delta, the characteristic of the equation. You've got the standard form of the equation is s squared plus 2 lambda omega something s plus omega something s squared, where omega is the natural frequency of the system, frequency of oscillation in the absence of friction, in radians per second. So that radians per second. So that's where the as in that other diagram that I drew in the last stream, where the line goes around and creates the circle. If you can do a radians per second is how fast that goes around the circle. If that number is large, well, it says it equals 0. Dampening ratio defined by where F is a critical friction. F is the amount of friction required to prevent oscillation. Friction would be like a resistance. Critically damped case. Okay, so if it's equal to 1, it's critically damped. If it's less than 1, it's underdamped. If it's greater than 1, it's overdamped. Oh, wait, what is this? Response. Consider the case with input shaft. E to the minus 2t has a time constant of 1/2 s. The natural response consists of two exponential terms which decay in the time constants. The system time constant is the longer of the two 1/2 s, so that the system reaches steady state in 2.5 seconds. As a Laplace transform solution. If we continue on, the time constant of the system, the time constant of the exponential is in envelope e to the minus t, which in this case has a value of 1s. Therefore, the system reaches steady state in about 5 seconds. So the logarithm of e minus t, form of the transient response. Since this is an identity, corresponding terms must be equal. That sets the sigma figure to F divided by 2J, whatever the fuck that is. Shows the natural frequency does not depend on friction. This must be true since the natural frequency can occur only if friction is not present. Inertia, dampening, there's dampening chemicals on F equals that. If that figure is less than 1, the system is underdamped. Damped, not 0. The system will, because there is no friction, the system will oscillate forever at the natural frequency of 3 radians per second. And this particular, wait, what? Since lambda is less than 1, the system is underdamped. Sigma equals 0 is the first case where the sun is undamped because of the first system of 3 radians per second. Consider a second order equation thus. It's critically damped. The system will oscillate at 3 radians per second only if friction is raised to 0. The actual response is shown in figure 521. We don't want that. That's critically damped. Since lambda is listed as underdamped, overshoot occurs, and the system oscillates around the steady state value. As shown in figure 523. The oscillations occur at the frequency omega d damped frequency equals damped frequency times the square root of 1 minus sigma squared. If the system contains no friction, and that equals 0, the envelope is a decaying exponential form of e minus omega times t. The time constant, rho, is 1 over that value. For this example, is 0.67 seconds. The system settles at the steady state in 5 time constants. It's typical of a capacitor, but a capacitor doesn't have the oscillations. I contend that there has to be oscillations, or maybe not. Well, there has to be oscillations because the decimal portion of pi is a changing number from 0 to 9. Instead of using figures, most of the literature employs a normalized second-order response curve, etc., in which the ordinate is y over theta t over theta s, thus y equals 1, and the abscissa is this value. The normalized curve shown in practice is difficult to use. For example, suppose an undamped system yielded the result shown in thus. But how could the number 3.14159 well, that's close to 3, right? That's a percentage close to the value. Using the parameters thus, k equals 10, omega s equals the square root of k over j, which is inertia, gain over inertia. Responsive servo to disturbances. They're saying that figure is f over 2 times the square root of kj. K is a gain constant, j is an inertia, f is something due to friction. The friction value would be very low. Simple feedback system here. is the electronics part. SPR steps per revolution. Just do the motor. Lead Mike networks. This is electronics. It's a system. Radians per second is that omega factor, but if it's set to 0, stabilizing using rate feedback. The Laplace transform is s plus 5 times s plus 1. Response A, B, and C. The error is high, but the damping factor is very good. In an effort to decrease the area, K is increased to 20. E to the infinity equals RO divided by 1 plus KE, where the input is 5 degrees per step. If K sub E equals 1, the steady state error is given, etc. here, where K is the limit as E approaches to infinity. With the numbers in the Laplace transform, K sub E equals 1, E to the infinity equals 5 over 2, which is 2.5. We obtain the characteristic equation for the system. There's a feedback loop. So, you know what? The information that I'm getting out of this is the fact that I need another bite. And I'm gonna have to go back to sleep for another half an hour and let's look up Euler's number E. Let's do, well, it doesn't really. For example, square root of 2 is an irrational number, but it is not a transcendental number as it is a root of a polynomial equation, x squared minus 2 equals 0. So it's a really complex number that is not algebraic, that is not the root of a non-zero polynomial with integer, the best known, etc., 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 transcendent. history. So here's a sum from n equals 1 to infinity of 10 to the minus n exclamation point. K is fractional. Some k and 0. In other words, the nth digit of this number is 1 only if n is one of the factorials. So those are factorials, 10 to the factorial, etc. E to the a is transcendental if a is a non-zero algebraic number. Then, since in is equal to minus 1 is algebraic, so Euler's identity I pi must be transcendental, but since I is algebraic, pi must therefore be transcendental. This approach is challenged by properties, subsets. All right, the decimal part of a logarithm, mantissa. That went down a little wrong. Mantissa logarithm. Logarithm of numbers greater than 1 that differ by a factor of a power of 10 all have the same fractional part, known as the mantissa. Log tables need only show the fractional part now, a typical list of mantissa has 4 to 5 decimal places in the ranges. The integer parts called the characteristic, etc. Simply by counting how many places the decimal point must be moved, yada yada yada. Note that the mantissa is common to all of 5 times 10 to the 1. This holds true for any number x times 10I because this log equals this equals this, log of 10 to the x plus I. Since I is the constant, the mantissa comes from the log of 10 base x, which is constant for a given x. Oh boy. logarithmic scale. I need to go to bed. The pure logarithm named is often used to mean the natural logarithm. See, there's the lines. Expresses the limit of the ratio of distance between consecutive bifurcation. It's the ratio of the distances. But where does this number start, though? Limiting ratio to the next between every period doubling. A function of x parameterized by the bifurcation parameter. Where is x squared plus y squared equals Euler's identity? This is the complex system. When e to the I of x equals cosine of x plus I to the sine of x when evaluated for x equals pi, Euler's identity is considered an example of mathematical beauty. Well, I don't give a shit about that. There's a limit function. C over n to the n. Euler's identity states that the limit as n approaches infinity of 1 plus x over n is equal to minus 1. This limit is shown in the animation to the right. Those are approximations. What is n takes various increasing values from 1 to 100. Computation of is displayed. Why is pi in there? When x equals pi, what is x? What is x? This is the radius. This is I. Any complex number z equals x plus I y curve 0.xy on the graph is represented in polar coordinates. That's what I was trying to think of earlier. Oh shit, I gotta go lay down. Z equals r to the e theta. Yeah, but this e number is transcendental. Where n equals 2. N to the n minus 1 k This is not good. This is not good. Oh, come on! Where the hell's my fucking equal sign? I'm gonna lose it, I tell you, I swear to God. Oh my God, I can't find my fucking equals. It's right here. Why is it saying plus? I don't know, I can't find this stupid shit. Mantis is part of a logarithm. And I'm wondering, so the numbers, to be able to deal with those numbers would be dealing with a logarithm, but I don't really know, like, I'm missing something. There's the ellipse equation. A plus B, that's just a focus point. If A equals 1, x squared plus y squared equals 1. I'm not here to have fun. What is this? Oh, this is just a transformation. I'm assuming the origin. X squared plus y squared equals r squared. So well, there's a 3, 4, 5 triangle. So 3 and 4, it might show that here. They might give you this if we're lucky. Right here. Oh no, that's not it. General equation. Constant values. Special forms. H is I cosine theta, What about T, trigonometric identity? Cosine squared times sine squared equals 1. Jesus. For some reason I can't find what I'm looking for. It's a 3, 4, 5 triangle, however... So 3 is x, 4 is y, and the radius is equal to 5. So if x is t, and it's moving forward, how is it that this is what always boggled me. I gotta call it quits. See here, this picture? Okay, this is what bothers the crap right out of me.
We have all seen pure tones illustrated as sine waves, but each moment in the sine wave's formation has a different phase associated with it, from 0 degrees to 359 degrees. You can see the sine wave forming here, and the round protractor on the left shows you the equivalent phase at particular moments in time. If you use the various points on the rotation of the protractor and draw those points on the graph on the right, you can create a drawing of a sine wave.
So this is what a circle looks like in time. It takes time. Okay, so if you just draw a circle with no time, if time equals 0, there's a circle. But everything moves forward in time, including the fact that I've got to get out of here. So I'll continue this later tonight. The point is trying to study infinity and try to eliminate pi or find out where that shit's coming from, you know?